Hello everyone, welcome back. In this video, we'll be discussing about the last problem of yesterday's biweekly contest, minimum time to make array sum at most x. The problem is really harder than the usual hard Leetcode problems, and it is based on a technique called exchange arguments. If you have never heard about it, or if you haven't solved similar problems before, it is next to impossible to solve this problem during the live contest. So as always, I will start from scratch and will try to give intuition of each and every step in the entire journey of optimization. But as this problem is a little hard, there will be phases in which you yourselves need to pause and think a little bit to understand the proofs explained. Rest assured, if you stick till the very end, I am very certain that you will be able to understand this problem and learn at least one new things from this video. So with that, let's get started. The problem states that you are given two zero indexed integer array nums1 and nums2. Every second for all the indexes, value of nums1 of I will be incremented by nums2 of I. Now after this operation is done, you can reset any index of nums1 to 0. Now you can apply this operation any number of times, or basically you after every second this operation is performed, so you have to return the minimum time in which you can make the sum of all elements of nums1 to be less than equals to x. Now it might be possible that you will never be able to make the sum of all elements of nums1 less than equals to x. In that case you have to return -1. So let's take one example. Let's say nums1 is 1 to 3, nums2 is 1 to 3, and x is 4. So basically you have to return the minimum number of operations or minimum seconds in which you will be able to make the sum of nums1 less than equals to 4. So currently at t equals to 0, the sum is 6 and 6 is not less than equals to 4. So you have to apply some operations and you return the minimum operations in which you will be able to make the sum less than equals to 4. So what they are doing is they will, after 1 second, what will be the state? So after 1 second, every element here will be incremented by nums2 of I. So this will become 2, this will become 2 plus 2 4, this will become 3 plus 3 6. Now notice you can also reset the element of any index of nums1. So what they have done, they have resetted I equals to 0. So the array was 2 4 6, they reset I equals to 0, the new array will become 0 4 6, right? So at t equals to 1, this is the state. Now after 1 second, again every index will be incremented by nums2. So this will become 1, this will become 4 plus 2 6, and this will become 6 plus 3 9. So this will become 1 6 and 9. Now again you reset this time I equals to 1. So the array would become 1 0 9 because you have resetted the second element. Now finally you again increment everything by nums2 of I. So this will become 2, this will become 2, and this will become 9 plus 3 12. And this time you reset I equals to 2. So this 12 will become 0. So the final array would become 2 to 0. And notice this array, the sum of every element in this array is 4, which is less than equals to 4. So in 3 seconds you are able to apply the operation in such a manner such that the sum is less than equals to 4, and you can try any other possible combination. So you can try, okay, I will not reset I equals to 0, instead I will reset I equals to 1 or I equals to 2 and stuff like that. You will not be able to obtain a sum of less than equals to 4 in less than 3 operations, and hence 3 is the answer. So hope the problem statement is clear. Now how to solve this? So let's say this is nums1 and this is nums2. Now we have to return the minimum time or minimum operation in which we will be able to make the sum less than equals to x, right? So what we can say, okay, I will start with 0. This is the minimum time possible, right? I will say, okay, is 0 possible, or is it possible to make sum of nums1 less than equals to x by applying 0 operation? If it is possible, 0 is the answer. If it is not, I will try with 1. Basically I will say again, after applying one operation, is it possible to make the sum of nums1 less than equals to x? If it is, then 1 is the answer. If it is not, then I will try with 2. Again for the 2 will again add the same thing. If it is possible to make the sum of nums1 less than equals to x by applying two operations. If it is, 2 is the answer, otherwise I will try with 3, and so on and so forth. Now notice one thing. The problem also says that it might not be possible to make the sum less than equals to x at all. So we have to stop somewhere, right? We can't keep on going like this. We have to stop somewhere such that, let's say we stop at p. So we have to find a p such that if p is not possible, then we can say answer is not possible. We will not try p plus 1, p plus 2, p plus 3. So basically we have to come up with a point wherein if after up till that point we are not able to make sum of nums1 less than equals to x, we can certainly say that sum will never be less than equals to x. So the next problem at hand is we have to find the maximum number of operations in which we should be able to make sum less than equals to x, after which it is not possible at all. So this is nums1, this is nums2, and now this is the table in which I have just incremented nums1 by nums2 one at a time. So basically this denotes the state at t equals to 1. Now notice that there was one more operation to reset a index of nums1, but we haven't made that operation yet, so that operation is remaining. So basically resetting is the only variable here. So if you see, increment every element by nums2 of I is common across the operations. Only operation that is variable is we can reset any index to 0. Now let's say we have 4 operations. We are doing 4 operations. So now there are various possible choice of resetting. We can reset after one operation, we can reset index 3, or after 2 operation we can reset index 1. After 3 operation we can reset index 4, and after 4 operation we can reset index 1 again. Now notice that it is never optimal to reset the same index twice. Why? I would strongly encourage you to pause and try to prove this entire thing, this claim by yourself. So let's look at it. Let's say you reset the first index at the second operation, or at t equals to 2, and you reset the same index at t equals to 4. So what is the final contribution? So final contribution, this index will be giving 0, right? Now you have resetted this index previously as well, but if this reset doesn't contribute anything here, rather it is worse. Why? Because with this operation you have reset this position, but you have added something to each of these positions. So in this particular case you have added 3, 2, 3 and 1 to each of the position respectively. So basically in the total sum that you will be having at the end, you will have 3 plus 2 plus 3 plus 1 extra. You can simply avoid this extra sum by not doing this operation at all, and you can say I will always do the reset once, and that too at very last. So basically what we are saying is, if there are more than one reset, if we are saying that okay, it is somehow optimal to do reset twice, we can simply remove the first reset and do the last and keep the last reset, and that by doing that we will be guaranteed that the sum at the end will be less than equals to what we would have if we would have done the reset twice, right? So hope this point makes sense. Now with this point, can we say that the number of operations, maximum number of operations possible is n? The answer is yes. Basically we can simply, what is the best thing that can happen? The best thing that can happen is we can have 0 at each of the indexes. So basically we will reset each index at max once, right? So there are total n indexes. So we will be able to reset different indexes n number of times. So after n, if we reset again, let's say after n we try to reset again. Now because every position is being reset at least once, you will be repeating one of the resets. So let's say you pick this particular thing. So you pick this reset will be a repeat of this. And we have said previously as well that if this is the case, we can simply remove the previous reset and the answer we will be getting will be less than equals to what we would have got with this reset, right? So what we are saying is with just n operations, if we are not able to make the sum less than equals to x, we will never be able to make the sum less than equals to x. Okay, so because after an operation we will be repeating the resets, and if we repeat the reset, we already proved that if we repeat the reset, the sum would be greater than what we would have got if we don't do the reset, right? So if we do one reset again, whatever sum we will get will be greater than whatever sum we already have. Now if whatever we already have is not less than equals to x, how would it be less than equals to x if we add something to LHS? It will never be, right? So that's basically the idea. The maximum number of operations is n. What does this mean? This means that you will keep on iterating over the indexes. You will try 0. You will say, okay, is 0 possible? If yes, then 0 is the answer. If it is not, you will try with 1. Is 1 possible? If 1 is possible, 1 is the answer. Otherwise 2, 3, you will go all the way up to n. You will say, is n possible? If n is not possible, then you will simply return -1. You can say, if n is not possible, or if after applying n operations you are not able to make the sum less than equals to x, you will never be able to make the sum less than equals to x. So this is the first part. So we have to now tackle the second piece, which is we have to sum for a given I. We need to figure out whether it is possible to make the sum less than equals to x by applying I operations, because that's what we need to answer in each of these iterations, that after applying some operations, is it possible to make the sum less than equals to x. So that's the next problem. Can we get a sum less than equals to x after applying I operations? So again the same thing. What we would have, let's say I is 3 in this case. So that basically we are saying that after applying 3 operations, is it possible to make the sum less than equals to x? So after 3 operations, the sum would be constant without the reset. Again, reset is the only variable. Everything else is constant. So without reset, the sum would be constant. And what would be the sum? Sum would be n1 plus n2 multiplied by number of operations, because n2 would be added those many number of times. So if you are doing 3 operations, n2 would be added 3 times to n1. So this will be the total sum after applying OP number of operations, right? Now this sum is constant. Now if you remember, there is just one more variable. Variable is we can reset some of the indexes. So let's say we reset this particular index at t equals to 1. So if we reset this particular index, the entire sum would be reduced by 8, right? Let's say we reset this index at t equals to 2. So again, the entire sum would be reduced by 7. And let's say we reset this at t equals to 3. So entire sum would be reduced by 6. So basically what we are saying is, based on what we reset, the sum, like we have to subtract something from the total sum, right? This is total sum, but because we have reset, this 14 would not be 14. Instead, this will be 6, because we have reset this here. So we will add 3 and add 3. So we'll get 6 here instead of 14. So basically, whatever we are resetting, that will get subtracted from the final sum. So we will subtract something from the final sum, and we want this thing to be less than equals to x. If this is less than equals to x, then only we can say it is possible to get a sum less than equals to x with I number of operations, right? Now, this is variable and these two are constant. So what we want this thing to be as greater as possible. If we somehow get what is the maximum value that we can subtract, and if s minus m is not less than equals to x, then it is not possible at all to make the sum less than equals to x with just I operation, right? Just to reiterate this part, if we are like, we have to select 3 elements. If we are able to select the 3 elements which can give us the maximum sum possible, and if we subtract that maximum sum from S, and if this number comes out to be greater than x, then you can safely say that it is not possible to make the sum less than equals to x with I operations, right? So the reduced problem now is you have to select some indexes, or in particular 3 indexes, 3 numbers from this grid, such that the sum is maximum possible. There is one more constraint. The constraint is you can't select 2 numbers from the same column. Why? Because if you select 2 numbers from the same column, it means you are resetting that index twice, and that is something we have already proved that is not an optimal thing to do. So we will never be resetting same index twice. In other words, we will never be selecting 2 elements from the same column. So this is the new problem. We have to choose 1 element from each row. We have to make sure that only 1 element is chosen from every column, and we have to do this thing in such a way that the sum is maximum possible, right? Now, how to solve this in the brute force manner? So what is the brute force way? Brute force way will be to try out every possible combination, right? How many combinations are possible? So there are n possible choice to pick an element from the first row. Let's say you pick some element from the first row. Now from the second row, there is n minus 1 possible choice, right? Because you can't take this one. This one is now gone, because if you take this one, this will, because you have taken index in second row, second column already. Second column is now free. You can only select between these 4 columns. So that's why n minus 1 choices. And finally, for the third one, in the same fashion, you will have n minus 2 choices, and so on and so forth. So basically, if you think about it, there are n factorial number of different combinations, right? Now, obviously, this is a very bad solution, in the sense that it will not pass the given time constraint, because n is very huge. Like 1000 is very huge for n factorial to be passed. So we need to optimize this. Now, how to optimize? A very simple recursive way exists to optimize this. I would strongly encourage you to pause right away and try to think of how to do optimization using recursion by yourself. So hope you have thought about it at least once. Now the idea is simple. Let's say you pick one element from here. Let's say you pick this particular index. Now what you want now, what is the maximum possible sum you can get with this particular grid? Isn't this problem exactly similar to the original problem? Original problem was, what is the maximum sum possible in this particular grid? Now the new problem is, what is the maximum sum possible in this particular grid? This problem and the original problem is exactly similar. It's just that the new problem is a reduced version of the original problem. Original problem has 3 rows and 5 columns. The new problem has 2 rows and 4 columns, right? So hope you can see the recursion here. So what will be the recursive call? Basically, you have 5 choices here. Now based on which choice you take, let's say you pick this particular index. If you pick this particular index, in the next iteration you will have 4 columns and 2 rows, and these are the 4 columns you will have, and this is the 2 rows we will have. So you will have 11, 6, 7, 9, 14, 6, 10, 10, and you have to pick one element from each row with this constraint, such that the sum is maximum possible. So in other words, this is how your recursive function would look like. Basically, let's say you have a function f which takes in the row which you are trying to fill, or in which you are trying to take an element, and you have is taken as well. Basically, this is to make sure that you don't take an element that is already taken before, right? So basically you don't take an element from the row that is already taken from before. So what you will do, you will for the first row you have 5 choices, right? So what you will do, you will try out every possible 5 choice. You will say, okay, if I take this row, either if I take this particular number, then the value or the final sum would be 8 plus f of row plus 1 with new is taken. New is taken will have is taken of 0 as 1 because you have taken the 0th column already. In similar fashion, if you take this one, you will have 6 plus f row plus 1 is taken. Again, this is taken is the updated is taken where you have updated the first column to 1 because you have taken an element in the first column. In the similar fashion, you will have other combinations as well, depending on you take the third index or fourth index or fifth index, right? Now this is the total value, or this is the maximum value you can get if you take the first index from the first row. This is the maximum value you can get if you take the second index from the first row, and similarly third index, fourth index, fifth index. Now we want maximum value for this particular thing, right? Basically we want what is the maximum value possible. It doesn't matter which row or which column you pick in the first row. So you will just take the maximum across all of these numbers, and that will be the final output. So the pseudocode for that would look something like this. Basically you will have row and is taken. Is taken is just a boolean array of size n where each index denotes whether you have taken that particular column previously or not, right? Now if you have like filled all the columns or all the rows, like if you have reached the last row, you will simply return 0. Otherwise you will try to fill this row. Now which all elements you can fill this with, or which all index, let's say you are trying to fill this particular row, so which all are the valid candidates? The valid candidates are the one which are not already taken. So if there is an index which is already taken, you will simply continue. Otherwise, this is a valid candidate. The ith index is a valid candidate, so you will try to pick I. Now if you pick I, this will be the sum, or this will be the maximum value for the remaining rows. Now for all such I, you will take the maximum, and that will be your final result. Now what is the time complexity of this entire solution? Time complexity would simply be, again, this is I am assuming that you will do memoization, because without memoization this will be exponential only. But with memoization, what is the time complexity? Basically you will, with memoization we are ensuring that we will not compute same state twice. So we will compute one state exactly once. So the complexity would simply be number of states multiplied by what we are doing in each state. So for a particular row comma is taken, we are doing order n operation. We are iterating over a loop that will run for n number of iterations. So basically for each state we are doing order n operation. Now how many states are there? Number of states would be number of distinct values of rows multiplied by number of distinct values of is taken array. Now number of distinct values of rows can be n, right? There can be n possible rows. Now is taken is a boolean array. So this will be, is taken is a array of size n where each index denotes one column. So this will be of size n, and each index here can contains either 0 or 1, where basically it will denote whether it is taken already or not. So total this has two choice, this has two choice, this has two choice to fill. There are two ways to fill this particular index. So in total there will be 2 power n number of possible is taken array variation. So 2 to the power n is the total distinct value of is taken array. So overall complexity of this entire algorithm is n square into 2 power n. Now surely this will also not pass the given time constraint, because n is up to 1000. So 2 power n is something which will not which is not meant for this particular problem. So we need to optimize this, and this is the crux or the heart of this solution, which is exchange arguments. So we have to remove this 2 power n from the complexity. Now where this 2 power n was coming from? This was coming from the is taken array, right? Now why we need is taken array? Because we need to somehow we need to capture the state that which all indexes are taken previously. Now you can see at this index or at this row you are filling the last column, but at this row you are filling the first column. Now because you are not filling the column in a ordered manner, you require to maintain this is taken array to ensure which all columns are taken. But if you have somehow maintained the order of columns as well, we can remove this is taken array very easily. What does I mean? It means we mean that if we somehow say that okay, if I have taken a particular index I at this particular row, let's say at row 1, and if we can somehow say that okay, I will never take any index less than I in row 2 or row 3 or row 4 or anything, basically any row greater than 1, I will never take an index I. If we are saying this, then this solution can be optimized very easily to something like this. So we can simply, instead of maintaining is taken array, we can simply maintain what is the last index that we have taken. And as we are saying that for any next row, we will be taking only the indexes after the last taken index, we can simply remove this is taken with last index that we have taken, and inside this we can instead of iterating everything from 0 to n and then figuring out which all are taken, we will simply iterate from last index plus 1 to n, and we will try out every possible combinations. So with this, the complexity has drastically reduced to order n square. This is still order n, and number of state is now order n square. So complexity is now drastically reduced to order n cube from n square into 2 to the power n. Now for this to work, you can't simply say this particular assumption, right? Why? Because it might happen that the optimal choice that you will be having requires one element from here, from the first row here, second element from the second row here, and third element from the third row here. It might be possible, and if that's the case, this approach of making sure that we are not taking any elements before at the next rows will not work. So to make this approach work, we need to somehow sort this array or sort this indexes. So we will say if we can somehow sort this columns such that this property is satisfied. Basically we are able to say if we have taken a index I at any row R, it is not at all optimal to take any index less than I for any row greater than R. So the new problem is we need to somehow sort the indexes such that this constraint is satisfied. Basically if we have taken a index I at a row R, it is never optimal to take any index less than I. Sorry, it is never optimal to take any index less than I in any of these rows. So in any of these rows, you will only take indexes which is greater than I, right? So if you are able to somehow sort these numbers in this fashion, that this inequality is always true, notice the word always, then you can apply that algorithm, right? Because then you are sure that if it is not optimal to pick anything before the last index that have been taken already, why would you take that? Because if you we are already saying that it will be optimal to take only the indexes which are after I on the previous index. So let's see how we can sort the array such that this inequality is always satisfied. One thing to note is you will not always be able to sort it in such a fashion. In this problem, we are able to do so, and how? Let's see. So we are incrementing by 2. So n2 of 2 is 2 and n2 of 3 is 3. So we are incrementing every time by 2 in this column and incrementing every time by 3 in this column. Now let's say you have removed this I at rth row and you have removed this this I plus 1 in r plus 1th row. Because you have removed or reset, initial value doesn't matter at all, right? Because you have already reset, right? So initial value already is gone. Now what will be remaining? Remaining would just be this increments. So basically you are saying that you will be incrementing 2 thrice. So the remaining value would be a multiple of this 2, right? Similarly, what will be remaining here? Again a multiple of this 3, right? So if you, because this the final value would be a multiple of 2 here and a multiple of 3 here, which one will you reset first? Let's say you reset 2 first, so this particular row column first, so you will have 2 3 number of times. Now you reset 3, so you will have 3 2 number of times, so you will get 6 from here and you will get 6 from here as well, right? Now let's say you have done this thing in opposite order. Basically instead of resetting the rth row at ith index at rth row, you are resetting I plus 1th index at rth row and ith index at r plus 1th row. So in this particular case, what is happening is you are incrementing 2 twice and you are incrementing 3 thrice, right? So in other words, you are saying that 2 will be incremented twice, so you will get 4, and 3 will be incremented thrice, you will get 9 at the end. So which of these two choices are better? The answer is the first choice is better. Why? Because you are resetting. After reset, only the difference or the value in n2 will matter, and whichever has greater n2 value, it makes sense to reset it at a later stage, right? Because if you reset it at a earlier stage, we know that this value would be contributed at least one more time than this value, right? So because of this, the final sum that you will be getting will be always greater than what you would get if you have reset the smaller one before and the larger one after. So again, this is the main part of the problem. Basically what we are saying here is it is always optimal, because after reset initial value doesn't matter, because after reset everything is 0, so initial value whatever was there doesn't matter at all. What will be remaining is just the increments that we are doing at every state. So at every stage or at every second we are doing an increment of n2 of I. So whichever has greater n2, it makes sense to reset that at a later stage than the one which has smaller n2. Because if we have just seen, if we reset the smaller one afterwards, if we reset the smaller one at r plus 1, which is after the larger one 3, then the final sum would always be greater, because this the previous reset would give us more, will be contributing more number of times than the smaller reset, or than the smaller r. So because of this, we can say that it is always optimal to reset the larger value or the value with larger r at a later stage. So in other words, we can say if we sort this array with the value of n2, so let's say we sort this array with value of n2, so n2 0 1 2 3 3, and with 0 there is 6, with 1 there is 7, with 2 there is 4, and so on and so forth. Basically we maintained the order of n1 and n2 simultaneously. Now if we sort this in this fashion, now we can say that if at rth row you have taken ith index, let's say, it will never be optimal to take I minus 1th index at r plus 1th row or any row afterwards, right? And because of this case, because of this inequality, we can convert this particular algorithm to something like this, right? So let's just look at it one final time. So we have sorted the array. So we have sorted this array to something like this, right? So 6 7 4 1 5 and 0 1 2 3 3. So we have sorted with n2. Now after sorting with n2, this will be the array, right? Now what we are saying is, this has a property that if we reset any element, or if we take any element, let's say we take this element at this particular row, it will never be optimal to take a lesser element at a greater row. So let's say you take this row, this element here, and you are saying that this element or this r plus 1th row will give, if you take I minus 1, this will give you larger value. So what you can instead, if you seek this will give you 6 plus 9 15. Instead, if you just swap it, then you will get 8 plus 8, which is 16, which is greater than 9 plus 6, right? So basically, because of this property that larger r will be should be taken afterwards, it is always true that for a single I, if you have taken an I at row r, for any row afterwards, you will never take any I before. So all of these I will not be a probable candidate for any of the rows before, any of the rows after this, because if they would have been probable candidate, you would have not taken I here. Instead, you would have taken I somewhere down, right? So hope this entire thing makes sense. So with this, we are able to convert the algorithm to something like this, and this was the main part of the problem. Now once you have converted this to this, notice that initially the solution was order n square to the power n, and with this the complexity is now just reduced to order n cube. And if you remember, this entire algorithm we were doing just to figure out what is the whether we can get, or whether it is possible to make a sum less than equals to x with I number of operations, right? So just to remind you this part, we have said that we want to figure out whether we can get a sum less than equals to x with I number of operations. So for that we have said that the sum is finally fixed. We just have to figure out what is the maximum sum that we can take, or that we can subtract by resetting the elements. So that's where we have solved this problem, wherein we have to find out the maximum sum possible if we take one element from each row and we don't repeat element from a single column. So that problem we are now able to solve in order n cube time. Now even n cube is not acceptable because n is 10 to the power 3. We need to optimize this as well. Now if you are watching this channel for some time, I am very sure that you will be able to optimize this n cube solution to n square by yourself. So I would encourage you to pause and try to think at least for 5 to 10 minutes by yourself how to optimize this n cube to order n square. So the solution is very straightforward. We are saying that at this particular row, we will start our journey from last index plus 1, right? Now we are fixing what will be the value of this particular row here. Now instead of fixing what will be the value of this particular row here, we can simply say whether like this index can either be taken in this particular row, or this index will not be taken in this particular row. So instead of fixing what will be the index at this particular row, we are simply saying either this index will be taken in this particular row, or this will not be taken. So if this is taken, what is the case? Basically, you will get this particular value for this index, and for the remaining rows you will figure out what is the maximum value possible, right? If you don't take, then what you are saying is, for this row I am not taking last index plus 1. So let me try with next index. So I will see with the next index, and finally we will take the minimum across these two, and that will be the answer. So with this, the complexity is simply reduced to order n square from order n cube, and order n square will surely pass the given time constraint. So just to reiterate the complete algorithm again, if you remember, we have said that we will start from n equals to, we will start from 0. We'll say if it is possible to make the sum less than equals to x with 0 operation. If it is possible, then 0 is the answer. If it is not, I will try with 1. Basically, if it is it possible to make the sum less than equals to x with 1 operation. If it is possible, then 1 is the answer. Otherwise, I will try with 2, 3, and all the way up to n. Because after n, if it is not possible, then the answer is not possible at all, and we will return -1. So this is what we are doing. We will try everything from 0 to n. Now, for every operation, we need to figure out, or for every I or OP here, we need to figure out whether it is possible to make the sum less than equals to x with this OP. And we have seen previously that the sum is s minus something, right, where s is fixed. Now this, what is the value of this s? S is basically n1 summation of n1 I and plus n2 I into OP, right? This is the value of x s that we have looked at previously, right? So from this x we will be subtracting something, and if this value is less than equals to x, then OP is possible, otherwise OP is not possible. So we want maximum value here, and this maximum value we can figure out with this particular function. Now there is just one small thing that you need to take care of. So if you do this algorithm, this entire thing would run in order n cube time. So basically, if you do this and this, the entire thing would run in order n cube time. This will take, you are iterating over n indexes, and you have n square algorithm within n indexes, and this will be running in order n cube time. But you can simply optimize this by reusing or by calculating everything here previously. So you can simply calculate all the values for all the rows and last index before even entering into this function. And once you have all the value for all the rows and all the indexes, this part would just be an order 1 operation, because you have already computed it. Now computing for all the values will take order n square time, right? Now this computation, you will, like, if you here, for simplicity, I have explained you with the forward tracking. Basically, we are filling the rows from 0 all the way up to OP. But if you think about it, if you fill the rows from 0 to OP, you will not be able to reuse the value of f of row comma last index. Instead, if you fill it in opposite direction, basically if you say, okay, I will fill from OP to 0, then you can simply reuse everything in between. So the only difference is the edge case, because OP is a variable here. The value of this function can't be reused across the different value of OP. So what, instead of going from top 0 to OP, you can simply go from OP to 0. In that case, this will be constant. Like now there is no OP at all here. So there is just the two variables, and you can reuse the value of f of row comma last index across various OPs, and that's where you can simply pre-compute everything before in just order n square time, and this entire thing would run in order n. So overall complexity is order n square, right? Now, one last thing. If you think previously what we are doing, we are saying that we are doing a linear search over OP, right? So in problems like this, where we are doing a linear search, sometimes binary search are applicable as well. But in this particular problem, binary search will not be applicable. Why? Because this is not a step function. Uh, I would encourage you to think why binary search is not applicable by yourself. That is very straightforward. That you can do as an exercise, and we can discuss if required in the comment section below. So with this entire algorithm, we are able to solve the given problem in just order n square time, and that will pass the given time constraint for sure. So I would encourage you to pause and try to code this entire solution by yourself. We have already looked at the pseudocode. You have to just code this out with a memorization function. So next we'll look at the code, and then we will look at one last time about this entire walkthrough. So the code is straightforward. We have this two function maxsum, and this is the actual main function. So we have just maintained a global array nums1 and nums2 in the global array n1 and n2. Now, as discussed, we will sort the array so that the inequality, this particular inequality, is satisfied always. Basically, if we are taking an index I at row r, it is never optimal to take any index less than I at row r plus t, right? So for this, we just sorted the array based on n2. So first number is n2. Now once we have sorted the array based on n2, we are sure, like now we are sure that we will take like the smallest n2 at the smallest possible index. So basically this inequality is not satisfied. Now after that, we just initialized this array n1 and n2 with the sorted values, and after this we are iterating over the operations one by one. For each operation we figured out the sum. Now this sum you can do, you can figure out by just iterating over it. So this we iterated over all the indexes j and figure out what is the total sum possible. And if you remember, the final value was sum minus the maximum value you can get by resetting the numbers. So we just call maxsum with op comma n minus 1. So op denotes what is the last row that you need to fill, and n minus 1 denotes that for the last row what is the maximum index that you can fill. So basically in this, if you think about this, it is saying that if you have to fill 3 rows, it's saying for third row you can start from here. Now let's say you picked this particular thing for third row. So you will, for second row, you will not pick this or this because of the same reason. Because if you pick this for second row, it is always optimal to exchange these two, right? So you will not pick this particular thing, and instead you will pick everything that is before the already picked index. So that's what we are doing. We either will not pick any index. So either for row r we will not pick this particular index. In that case, we'll say the value would simply be row r comma last index minus 1, or we will pick this particular index. So if you pick this particular index, then for anything before you have to start from for anything before you can only take these all indexes. Any index after I will not be a valid candidate. So that's what we are doing. We figure out the value of the current position and simply do maximum of row minus 1 comma last index minus 1. So basically we are saying for we have to fill this 2 rows now where the last row can start from last index minus 1, right? So this entire thing will run in order n square, and we have just simply memoized it so that we will not compute the same thing again and again. And one more thing to note here is we are not resetting the DP array inside. So this entire n square thing will be reutilized over and over. So in over this entire lifetime of this loop, this function will be called n square number of times at max, and hence the entire complexity is just order n square. So that's the entire solution. Let's quickly do a walkthrough of the entire thought process before we close out. So we started by saying that we have to figure out the minimum time required. So we say, okay, because we need to find the minimum time, we will simply start with 0. We'll say, is 0 possible? In other words, is it possible to make the sum less than equals to x with 0 operation? If it is possible, then 0 is the answer. Otherwise, we will try with 1, 2, 3, all the way up to some p. Now, this p should be a constant value or should be a deterministic value, because it might be possible that answer is not possible at all, or we are never able to make the sum less than equals to x. So for that we need to figure out what is the deterministic value of p. Basically, what is the value after which we will, if the answer is not there, we can say the answer is not possible at all. So for that we saw that resetting the same index twice doesn't make sense. So only variable in this entire run of the algorithm is which index you are resetting, and we saw that resetting the same index twice doesn't make sense at all, because if you reset the same index twice, you are adding more elements to your bucket then you are because if you are anyway resetting this element afterwards, so with this operation you have added more elements to your final sum, which is definitely not optimal. So that's where we saw, because resetting same index twice doesn't make sense, we can reset each index at max once. So in n operations we can reset every index at least once, and hence after after an operation, if we try to reset anything, we will be resetting it twice, and we have already shown that resetting it twice will not will make it will add it to our sum, and because we are adding something to our sum, it will never be less than equals to x anyways. So that's where we saw that the maximum value that we need to iterate up till is n. Now the question was how to figure out whether we can get a sum of less than equals to x with I operation. So for that, what we have seen is the sum is constant. Only thing that is variable is which part we are resetting. Now depending on which part we are resetting, we will be getting something to subtract from s. Now the final sum would be s minus something, and we have to for this statement to be true, we need to make sure that s minus something is less than equals to x. So what we have said is we will just simply figure out what is the maximum value of this something, and if s minus that maximum value is not less than equals to x, then this statement will never be true for I operation, otherwise this statement is true. So for that we went ahead and to find out, we have to choose one element from this row, and we can only choose one element from a single column, because we can't reset the same row twice. And because of this we came up with a very nice straightforward recursive solution that will run in order n square into 2 to the power n. Now this solution will not pass the given time constraint. So what we have seen that we can rearrange the numbers here such that it is always possible, or it is always optimal to say that if you have picked I at row r, you will never pick any I before you will never pick any I before this particular I in any of the rows afterwards. So for every row after r, you will always be picking the indexes which are greater than I. Now because it is possible here, we can simply reduce this n square into the power n algorithm into a simple n cube algorithm. Now for this rearrangement, what we have seen is why this rearrangement was possible, because after reset only thing that matters is n2, and we if n2 is the only thing that matters, it will always make sense to reset a smaller n2 before a larger n2, because if you reset a larger n2, so in this particular case this column has larger n2 which is 3. So if you reset this column before resetting a column of 2, the sum that you will be getting will be always larger than the sum which you would get otherwise if you reset this column first, right? So after this, we simply sorted the array in terms of n2, and we simply say that this algorithm holds true. Now after that, we simply optimize this order n cube algorithm to order n square algorithm by simply removing this for loop by saying that we don't need to find what will be the value of row r in this iteration itself. We'll figure it out along the way. So either last index is possible at row r or it is not possible. So we'll just take these two criteria and get rid of this particular loop. Now after this, we simply did the entire thing. We simply iterated over op from 0 to n and figure out the sum, which will be n1i plus n2i cross op, and then we figure out what is the maximum value that we can subtract here, and the maximum value we can figure out by this recursive algorithm. Finally, we looked at, okay, this op was a variable here, so because op is a variable, we can't reuse this function or the value that is computed previously across different set of ops. Basically, we have to reset the dp array inside this function always if there is an op inside this function. So we simply remove the op by iterating in the backward manner from last to first. So by iterating in the backward manner, we have removed this op, and hence now because there is no op at all, this function can be reused across different values of op. So this resetting the dynamic programming variable dp array can be done outside of this, which means this function will be computed which will be called at max n square number of times over the lifetime of this loop, and hence the complexity is just order n square instead of order n cube. And finally, we also saw that we can't optimize this linear search to binary search because this is not a step function. So hope entire solution makes sense. If you have any doubts in any of the piece, feel free to post them in the questions below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And finally, there is a nice lecture on this exchange arguments, and there are various follow-up problems as well which you can see if you are interested. But really, it is one of those techniques which might hardly come if you just do Leetcode. So I will link the blog post in the description as well so that you can take a look. So with that, I will see you in the next one. Thank you.